And I'm going to talk about this equivalence right now. So I have here, I have a covariant derivative. I have a derivative. The name covariant seem, if you want to look, like, again, better educated, you can say covariant derivative. It's just directional derivative. Sometimes you call it connection, like I said, a fine connection, maybe even more better educated. This is nabla. You have Riemannian metric. G. This is a way to measure distance. This is a way to differentiate on the manifold. Nothing more, right? This guy is completely characterized by gamma ijk. If I give you gamma ijk, I tell you completely how to do the derivative. Here, I just give you the matrix, right? What is the conceptual definition of straight line? Geodesic. Here, it's a curve with zero acceleration. I'm defining it in terms of acceleration because this is all what I can compute, derivatives. And here, it's shortest distance, right? Shortest path. Because all what I can compute is distances. So I'm going to pick the infimum of them, the minimum of them. Okay? So this leads to the following equation, the very famous equation, gamma prime is 0. This leads to minimization of L or E of gamma, which is a calculus operations problem, right? So from here you get a geodesic, and from there you get a geodesic. And the geodesic here is just dictated by nabla. We call it actually a geodesic of nabla. You give me a way to differentiate, I give you a geodesic, a straight line. You give me a way to measure distance, I give you a geodesic, another straight line. Okay? They may not be the same. Actually, here I can have many nablas. Each nabla has its own geodesic, and the same here. So, are they equivalent? When you get these two geodesics, are they equivalent? So far, no. But if nabla satisfies more properties, then they would be equivalent. What are these properties? Here's the first. Nabla is a metric connection. So come from the metric, respects the metric, if it satisfies the following. So this is the Riemannian metric acting on two vector fields y and z. What is the result? Yeah, scalar, right? Scalar, and maybe a function on the length. So here I'm differentiating it along x. So this should be g of nabla xy and z plus g of the other way around, y and nabla xz. In other words, this property is that both nabla and g respects each other. They are compatible. Actually, sometimes they call it compatible. Nabla is compatible with g is this equality holds. So second, nabla is symmetric. Sometimes we call it torsion free. Has zero torsion tensor. If what happens if what we expect, the Lie bracket between x and y is nabla xy minus nabla yx. Because not every derivative satisfies that. And if nabla satisfies both, then we have the fundamental theorem in Riemannian geometry. Given this guy M and G, manifold, a Riemannian metric. So we call it what? A Riemannian manifold. Okay? Given this guy, there exists a unique, symmetric, metric connection. is only one that is compatible with this G, i.e. there exists a unique nabla satisfying 1 and 2. It's only one. It's called the Lec12 connection. So without looking too complicated, you give me a Riemannian metric. Well, there is a connection there is a way of differentiation that is compatible with this guy. They respect each other, and it's symmetric. Symmetric means that this property is satisfied, and also means that the gamma ijk, they are symmetric. Okay? That's okay, but what we will benefit from this? What do we get? So now, look at this here. Look at these two lines, two columns. What was very hard here? What thing do you hope to get? When we have equivalence, we can take tools from here and benefit there, and vice versa. What was very hard here in this line? Gammas. So now we're saying that gammas, we will determine them from the G's. We said, you have seen now, we did an example to get the G's from the ambient space. It was very easy, right? So if you have the G, okay, I can tell you how to get gammas because they are compatible with each other. So gamma I, if this is the case, then here is the outcome. Gamma ijk is 1/2 summation L1 to N GKL partial GI, yes, L, partial QJ, partial G, the other way around, minus partial GIJ, partial QL. Give me the G's, I give you the gammas immediately. One thing that I must note here, that this is the inverse of G. So this is indeed G inverse, the KL element of it. And I will not do an example to get the gammas. It's straightforward here. This course is advanced, but if you want to see an example of how you compute one of these gammas from this definition in detail, you can go to the course 241, the last lecture, I guess, the lecture 18, part 3 and 4. Okay? You will see we do it step by step how we get one of these gammas. Okay? But you can program it. It's super easy, or whatever you like. Or actually, I don't do it this way. I don't like to do it this way. If you want to program it and make it algorithmic, that's perfect. But if I have a problem and I want to solve it by hand, I will not do it. I will never use this definition or this property. I will do it from here. Because I have the G's, I can get these red equations easily, and from the equivalence, I will read off the gammas like I show you now. Okay? On the other hand, what was also a bit hard in this branch? Well, the G's are okay, but to get the shortest path, I have to solve this calculus of variations problem. Well, we have an equation ready for them already. So now the geodesics are equivalent. And they satisfy this equation. So no need to go and write down the geodesics anymore. We have a coordinate-free expression for them. Any questions so far? Any question? Any question?
So, Professor, suppose that we have the Christoffel symbols and we want to get the G's. So this system of partial differential equations can be solved only if the two are compatible? If the Lec12
Well, this equation is not valid if they are not. Yeah. This is for the Lec12. Yeah, for the Lec12 connection. For a connection that comes from the metric. Okay. Again, I said this in 241, but it's super important, and I will repeat it here. So, relation to mechanics, I will give an example just to motivate the thing, and I will then generalize. And the example obviously on S2, because we have several results on S2. So this is again S2, X, Y, and Z, and this is very important, and it's not found. I don't know. I did not find it in a single source. You have to bring too many things. So this is your sphere, and I have a ball that is rolling. So this is a ball of mass, unit mass, rolling on the sphere, again with the same thing. So this is your theta, this is your phi, the same coordinates. So we already know my x, y, and z as a position vector is just cosine theta, cosine phi, sine theta, cosine phi, and negative sine phi. So mechanics point of view, I want to get the equations of motion, so I'm going to differentiate this guy, so please differentiate it for me. So for example, this is negative cosine phi phi dot, right? And then we write down the kinetic energy, 1/2 mr dot squared, do it and get all the things. So we get 1/2 m cosine squared phi theta dot squared plus phi dot squared, right? And we typically write down the kinetic energy as